Hello everyone, this is the presentation video for the ICRA 2024 paper, Weather Depth, Curriculum Contrastive Learning for Self-Supervised Depth Estimation under Adverse Weather Conditions. Depth estimation builds a bridge between 2D images and 3D scenes and has numerous potential applications such as 3D reconstruction or autonomous driving. The existing models have shown promising performance on clear scenes, but fail to generalize to adverse weather conditions like rainy, snowy, etc. To this end, we propose a self-supervised robust depth estimation model, named WeatherDepth, to address the above issues through curriculum contrastive learning with an adaptive scheduler. To train an expected model and shrink the domain gap to real weather conditions, we first simulate a weather-augmented dataset. Actually, weather comes in varying degrees and categories. So as shown in the figure, we combine GAN and PBR techniques to simulate the progressive advances from clear to relatively adverse, and then adverse weather scenes, building the simple to complex curricula datasets, named WeatherKitty. Building upon this, we first train a base model on sunny data with clear structures to satisfy photometric consistency. This allows the model to obtain better generalizable local optima for pre-training on more complex scenarios. Then we optimize the model on relative adverse weather images with light effects, ground snow, and water, which share a part of common regions with the clear domain and inspire the model to gradually grasp the depth cues against the missing textures and contrasts. Finally, we train the model on adverse data with the addition of weather particles, for example, raindrops, further boosting the capability of handling complex noise patterns and violations of self-supervised assumptions. Meanwhile, to prevent the model from forgetting previous curricula, we integrate contrastive learning. In the first stage, we establish one contrastive mode between two clear images with different traditional enhancements. The second stage builds three modes between the sunny scene and randomly selected rainy, snowy, or foggy weather scenes. The third stage constructs 9 modes with cross-weather contrast. These increasingly challenging contrastive modes not only formulate another curriculum learning process, but also prevent the network from solely focusing on resisting weather changes and completely biasing its domain to the new weather. And concretely, the detail of each contrast mode is shown as L-augment, where D-augment and D-contrast should be the same since they are the depth predictions from different weather augmentations of the same image. Here we assume the predictions from the previous level are more accurate for it has already well trained in the last curricula and stopped its grad to constrain the D-augment. The total loss is L backward, where L model is the self-supervised model loss, omega curriculum is the contrastive weight. Considering the model needs to adapt to weather changes when entering a new stage, we initialize it to a small value and increase it in each epoch. Besides, to reduce manual intervention and better adapt our method to different models, we designed an adaptive curriculum scheduler to automatically search for the best timing for course switching. Specifically, as shown in lines 8 and 10 to 14 in algorithm, we record and average the L model and set a patience for every stage. We move to the next stage when the L model difference between the current and previous epoch surpasses the patience threshold. To prove our method's expansiveness and effectiveness, we incorporate the proposed scheme into 3 baselines with huge differences and make extensive experiments on 1 synthetic and 2 real datasets. The quantitative results are shown in the following tables, and you can pause the video for details. This video mainly shows the qualitative results. On WeatherKitty, our following demonstration will be as shown in the figure. You can compare these 3 pairs of results to observe the effectiveness and generalization ability of our model. Also, you can compare this pair of results to see how our model performance surpasses current state-of-the-art models. Next, we show results on the CADC dataset. For scenes with raindrops on the lens, our model does not produce warped depths for trees and roads and is able to extract more details as shown in the last row. We found that the problem of incorrect sky depths is alleviated after our enhancements, and road signs no longer exhibit incorrect edge artifacts. Then, we show results on the driving stereo dataset. It can be seen that artifacts and incorrect depth cues caused by water reflections are corrected by our model. Finally, the summary of this paper is as follows. You can review our contributions by reading this page. Our code is open source on GitHub, as shown in the last link. Thank you.